Hey there, future physicists. Let me ask you something. Have you ever looked at a soda can and wondered what makes this can hold pressure? How is this system in balance? That, my friends, is all about thermodynamic state variables. In the world of thermodynamics, state variables are the essential pieces that define the state of any system at a particular point. These are things like pressure, P, volume, V, and temperature, T. Imagine you're on a roller coaster. The way you feel, how fast you're going, speed is equal to temperature, how much air is pushing against you, pressure, and how much room you have to breathe, volume, all depend on these state variables. And get this, you can determine everything about a system's state just by knowing these three. How cool is that? Let's take a moment to understand just how powerful these state variables are. Think of them like the coordinates of your location on a map. Just like latitude and longitude, pressure, volume, and temperature give you everything you need to describe a system. Here's the interesting part. The values of these variables don't depend on the path taken to reach that state. It's like traveling from home to a friend's house via different routes. You'll still end up at the same place with the same coordinates. The same goes for thermodynamics. Whether you heat the system slowly or quickly, as long as you end up at the same place, the pressure, volume, and temperature will be the same. Pretty nifty, right? Now, let's talk about the equation of state, the big idea that ties all these state variables together. The equation of state is like the secret formula that links pressure, volume, and temperature. It's the reason we can predict exactly how gases will behave when conditions change. One of the most famous equations of state is the ideal gas law, PV equals nRT, where P is the pressure, V is the volume, N is the number of moles of gas, R is the gas constant, T is the temperature in Kelvin. This simple equation tells us that for a given amount of gas, the pressure and volume are directly related to the temperature. When one changes, the others will react, just like how squeezing a balloon makes the air inside hotter. A little squeeze, volume, and the temperature inside spikes. So where do we see this equation of state in the real world? Let's talk about engines. The ideal gas law is what helps engineers understand the pressure and volume changes in a car engine during the intake and exhaust strokes. Similarly, refrigeration works based on principles derived from the ideal gas law, where gas is compressed and expanded to absorb and release heat. And the best part? Real gases don't behave exactly like the ideal gas law predicts, especially at high pressures or low temperatures. So, scientists and engineers use modified equations of state to make adjustments for those real-world conditions, making the ideal gas law the first step towards more accurate predictions. Let's apply this to a real-world problem. Imagine we have a gas in a piston. The volume is 2 cubic meters and the pressure is 1 times 10 to the power of 5 pascals. We want to know what happens if we increase the volume to 3 cubic meters, keeping the temperature constant. Let's use the ideal gas law, P times V equals N times R times T. Since the temperature is constant, the product of pressure and volume stays constant according to Boyle's law. So, we can set up the equation like this. P subscript 1 times V subscript 1 equals P subscript 2 times V subscript 2. Now, substitute the known values 1 times 10 to the power of 5 times 2 equals P subscript 2 times 3. Now, solve for P subscript 2. P subscript 2 equals the product of 1 times 10 to the power of 5 and 2 divided by 3, which equals 6.67 times 10 to the power of 4 pascals. So, after the volume increases, the pressure drops to 6.67 times 10 to the power of 4 pascals, as expected. This shows how pressure and volume are inversely related when the temperature is constant. To sum it all up, thermodynamic state variables like pressure, volume, and temperature give us a snapshot of a system's state. The equation of state ties these variables together and helps us predict system behavior. Whether it's gas in a piston, air in a tire, or fuel in an engine, these concepts are key to understanding how energy, pressure, and volume interact in the real world. I hope you now have a clearer picture of how state variables and equations of state work together to define and predict thermodynamic systems. See you in the next session with another exciting concept in physics.